It's not his first time speaking to us. He has been our guest speaker about a year and a half ago, and he's back again this time talking about outflow effects. So with no further ado, Doctor.
Well, thanks, Al. Thanks for having me back again. Let's start by seeing if I can share my screen, shall we? Okay, can you see that?
Yeah, looks good.
Great. I think I've met some of you, but perhaps not all. So a bit of my background might be in order. I essentially started my aerodynamic career back in South Africa in 1989 as a helicopter design engineer working on the rotors of the Rooivalk attack helicopter that was being developed at that time. And based on my industrial experience, which was largely that the tools that we had at the time were not really up to the job, I developed a lifelong interest in understanding the aerodynamics of rotorcraft. And much of that career has actually been in academia. I was at Imperial College in London and then moved to Glasgow University and then Strathclyde University. And throughout that time, I was involved in the development of models for helicopter computational aerodynamics and the application of that model to various problems which arose during the course of those years. So the one I talked about last time was the vortex ring state, where the accident in the early 2000s with the V-22 Osprey caused a big reversion of interest onto that particular phenomenon. But we've been doing other things as well. And some of the brownout research that we did in conjunction with Augusta Westland in the context of the Gulf War certainly motivated some of the work on downwash and outwash that I'm going to talk about in a little bit more detail this afternoon. Around about 2016, I decided, okay, enough of academia. Let's go and do something a little bit more interesting. And I founded Sophrodyne Aerospace in partnership with my wife, who's an accomplished computer scientist. So you can imagine the kinds of things that we talk about over dinner. Now, let's just get down to the basics and get a few definitions under our belt before we get any more complicated. Now, we know that helicopters, tilt rotors, and many other eVTOL aircraft rely on a set of propulsors to generate lift during their descent and landing. And that lift is generated by accelerating air downwards through the propulsors. So that pattern of downwards moving air below the vehicle is what we call the downwash field. And then when that flow hits the ground and turns outwards and is deflected radially out across the ground, we call that field the outwash field. So it's important to get this distinction, if you like, between downwash and outwash. Now, we know from our helicopter experience that outwash can be a problem. Various operational problems include uplift of debris, upset to personnel, damage to ground facilities. The root cause of brownout, if you like, is downwash and outwash. And so we're familiar with some of these problems within the helicopter community already. We also know that the environment is not necessarily the only part of the system that's afflicted by outwash issues. The aircraft can be influenced by the outwash characteristics of the system as well. So we know that there's some typical problems such as buffeting and vibration, reduced longitudinal static stability, changes in dynamic stability, all sorts of things like nonlinear control responses, for example, during accelerating the aircraft into forward flight, that are caused on the aircraft by its interaction with the ground and by implication with the outwash field that the aircraft creates. Okay, so some of the background work to this was work that I did on the vortex ring state in the context of vertiport design. And I'll return to the whole issue of vertiport design later. As you might imagine, the outwash issue is particularly pertinent when we get to that particular frame of reference. And the work that I presented at the EASA Rotorcraft and eVTOL Symposium, which you can find that presentation online, was called Are eVTOL Aircraft Inherently More Susceptible to the Vortex Ring State Than Conventional Helicopters? And that's very much what I talked about last time that I was invited to talk to the council here. And the key finding was that if you followed the EASA regulations as far as these quite steep approaches that they were considering mandating for approach into highly confined urban airports, then you might encounter problems with the vortex ring state. So the vortex ring state lives within this part of the flight envelope as defined by rate of descent and horizontal velocity. And generally, when you were operating within this cone-shaped final descent area, you were forced to operate in this very, very narrow bounded band of rates of descent, given at the highest rate of descent by the vortex ring state, and of course at the lowest rate of descent by simply staying in the air for an infinite amount of time. Now, the problem was that to have acceptable properties during that final state of descent, in other words, to avoid vortex ring state, you'd have to have a very low rate of descent. The problem was that if you hung around at a very low rate of descent, then obviously you'd exacerbate problems with ground interaction because your interaction with the ground would be prolonged. Okay, so that led to essentially the focus on the ground interaction, perhaps as ancillary issue to do with vertiport operations. And I'll talk a bit about that today. So I'll look at the basic physics. I'll look at some of the background to the work that we did. I'll describe in some detail the new study that we performed. And then I'll talk about perhaps the most interesting part, which is actually the practical consequences of the findings that we managed to come up with. So the problem can perhaps be encapsulated in the sense that we know that outwash is a problem with helicopters, but might eVTOL aircraft create a bigger outwash problem than with helicopters? And we know that the main factor influencing the strength of the downwash field, of course, is the disk loading of the propulsors. Now, this diagram, I think many of you have probably seen before. I presented it earlier, which shows how the downwash velocity is related to the weight of the particular aircraft. And what it does is it tries to contrast the properties of conventional helicopters, shown in blue, with some of the sort of more representative members of the helicopter class shown in yellow, with the characteristics of the eVTOL aircraft for which I could find data. And generally, it's clearly apparent that most current eVTOL aircraft have higher disk loadings than conventional helicopters with the same weight. So in other words, the downwash velocities that they will produce will be expected to be higher than those produced by similar sized or similar helicopters with similar weight. Okay, so how does that transfer into the outwash field? Remembering that we're talking about downwash and outwash as two separate issues. Well, the first thing to realize is, yeah, if you look at the downwash issue, then if you plot disk loading on the horizontal axis versus downwash velocity, you expect to see a trend like this. And helicopters indeed are fairly low downwash compared to eVTOL aircraft, but we do have considerable experience with classes of aircraft which have considerably higher downwash velocity. So tilt rotors live at the high end of the eVTOL spectrum, and then we have all these jet lift type vehicles or directed thrust vehicles over at the top here. Many of them not in service anymore, but of course they were de rigueur, if you like, during the 1970s and 80s. Now, when it comes to the outwash problem, we need to be a little bit more careful, in that size of the aircraft is critically important. You can imagine two different aircraft that are geometrically similar and are operating under geometrically similar flight conditions. So, for example, at the same ratio of the height above the ground to their characteristic dimension, if they have the same disk loading, those vehicles will have the same downwash velocity. But we wouldn't expect their outwash characteristics at the same distance away from the system to be the same. So in other words, there is a scaling issue here. There's an idea that the size of the aircraft actually makes a difference. So don't be too naive in terms of this idea that a high disk loading is inherently the only factor that controls the strength of the outwash. And in fact, the best thing to do is to take this diagram on the left here with the downwash velocity expressed in terms of the weight of the aircraft and to re-express all that information on a slightly more complex graph where we have disk area on the horizontal axis, weight on the vertical axis, and lines of constant downwash velocity are actually diagonally across that diagram if I plot on this log scale. And then what we can actually see is that that diagram evolves into a slightly more interesting state, in that we can perhaps partition up the eVTOL aircraft into separate classes. These guys down here in Group A are very small and very light, and so they are probably not a risk as far as their outwash is concerned. These guys are heavy and small, and hence we don't really know how they're going to behave. We need to do further investigation. But perhaps the aircraft that are of most concern are these that are up here, which are roughly as heavy as conventional small helicopters, or even fairly large helicopters sitting here above the Bell 206B, but they're a risk in terms of both their weight and their size as a result. So whichever aircraft you happen to be flying, it might fit into one of those classes there, and we need to be a little bit careful about which one we're actually considering. Now, given that downwash and outwash are two distinct phenomena, how do we actually relate the two? So this diagram tries to encapsulate this. We have the downwash, which comes through the rotors, that hits the ground and spreads out and turns into an outwash. But how do we actually relate the downwash to the outwash, and hence the outwash to the disk loading through of the system? And I'll talk about that in detail in the next few slides. A lot of the information that I'm going to present from here on is encapsulated in this new study, which was completed under UK Civil Aviation Authority and is now published and available on the web as CAP 2576. And this study was really intended as a first step, really, towards understanding the issues more broadly. I think that's worth keeping in mind. It was a stab in the dark, if you like, an attempt to add some more information into the mix, but certainly it wasn't seen as the last word on the subject. It was really there to try to engender a bit of discussion and a bit of a to and fro as to how important this issue really would be for eVTOL aircraft as we currently understand them. And what the study does is it integrates existing knowledge and then into a consistent framework that we hope can help predict and explain the effects of outwash and downwash that might be associated with current and future eVTOL designs. And then we try and take that knowledge and extend it a little bit by producing new numerical data, which reveals the salient flow physics. And then what we do is we try to extend our understanding by applying this new knowledge to a range of eVTOL-like configurations. You'll see just how generic these particular configurations are in a minute. The intent was not to reproduce a Joby or a Vertical or a volocopter. It was really to be as generic as we possibly could and as careful in comparing these different configurations as we possibly could be, so that we'd end up with some sort of basic physical and scientific understanding, which we could extend more broadly across the range of eVTOL aircraft. Sources information, well, it's amazing how much information is actually out there. There's helicopter and tilt rotor experience. There's related work on multi-rotor designs. There's historical VTOL programs where the information can be almost ported directly into the new eVTOL domain. And then there's a whole load of information which was done in the context of jet lift largely by NASA in the 1950s, 1960s, and 1970s in support of various programs, which is readily accessible for access. Now, what do we already know? It's perhaps worth actually thinking about that. The whole industry of outwash and downwash is dominated by a very influential FAA Department of Transport study that dates from the early 1990s. The work originated with that of Ferguson, but then Preston and co-workers extended that. And what they basically did is they thought of the downwash as this flow through the rotor, which would then turn into a jet-like flow, a thin jet-like flow out across the ground. And this idea has very much informed how people tend to think about the outwash field in current circumstances. So the flow has this jet-like nature, on top of which perhaps there's certain perturbations, and that's essentially it. It's a very sort of orderly picture of what actually goes on within the flow. And as the flow moves out across the ground plane, it effectively decreases in intensity. The velocities get smaller and smaller, and perhaps the fluctuations on top of that mean flow get smaller and smaller as well. And eventually the flow dissipates into the far field. In terms of what we know for multi-rotor vehicles, this is the typical diagram that you'd find in the work by Preston. Basically, we know that if you have multiple rotors, then the flow actually changes character quite distinctly. It becomes highly directional. The flows become higher than the mean flow in certain parts of the flow field and significantly more unsteady, particularly where the flows from the various rotors coalesce. And this is an issue that the helicopter world has had to contend with to some extent. For example, if you're a CH-47 pilot, you'll know about jet-like flows outwards along the periphery of the outwash field, but it's not something that's particularly well within the lexicon of standard helicopter type analysis. Okay, so we want to extend beyond this level of understanding. And what we expected is, yes, that if we ended up with multi-rotor configurations that are typical of eVTOL aircraft, you might end up with a very non-uniform flow fields of very high magnitude along certain parts of the azimuth with respect to the vehicle if you have a multi-rotor configuration operating at low altitude above the ground. And that was effectively the position that was taken. And the way that we would encapsulate that particular variation is we would say, okay, that's the velocity out across the ground, that's the induced flow through the rotor, and perhaps you'd have to define this function, which we'd call an amplification factor, which is a function both of radius and azimuthal position around the vehicle. And these two examples here, this is a quad rotor compared to a conventional helicopter. Here you can see there's not much variation of the velocity around the azimuth, but here you can see that there are very certainly certain directions along which the outflow is concentrated. Okay, if we went to forward flight, then we know that things get really, really interesting. And that is that the structure of the outwash field as produced by a single rotor helicopter depends, of course, on the height above the ground at which the aircraft happens to be flying, but also its airspeed and the strength of prevailing winds, with this very interesting physics that the flow can actually change modes depending on the speed at which you're traversing with respect to the air. And so in transition to forward flight, you might encounter the flow changing geometrically through a variety of patterns. And the one of most interest to us is this highly recirculatory flow regime, which develops into this idea of a ground vortex as you pick up speed across the ground. So this idea of several modes. And the modes you can actually encapsulate in a diagram like this, which I call the Curtis diagram in honor of Pat Curtis, who first came up with it, where essentially as a function of forward speed on the horizontal axis and rotor height, you'd be able to pick up the flow in these various flow modes. And here's quite a beautiful picture of a CH-53 flying at low altitude across the desert. And you can see this beautiful bow-shaped ground vortex existing in the flow just upwind of the vehicle in those conditions. Now, what happens when you take this helicopter type information and transplant it into the multi-rotor field? Well, what we expected and what we found is that the helicopters in general, or eVTOL aircraft with their multiple rotors in general, have a much larger footprint on the ground than comparable helicopters. And this is again a consequence of the aerodynamic interactions between the rotor wakes. So in this quad-rotor vehicle here, you can see these almost like these twin bow vortices or bow vortices, which interact to create a very broad structure upwind of the aircraft as it moves along the ground. And another interesting thing here is, of course, the amount of turbulent structures that tend to interfere with the tail structures, the empennage of that particular aircraft. And I'll perhaps get around to talking about that in a little bit more detail. Okay, so how much stronger will the outwash in fact be compared to a helicopter with the same weight? Well, this is the kind of analysis that we would do. We would take the helicopter outwash velocity, amplify that by a disk loading effect, so just accommodate the difference in disk loading between your typical helicopter and your eVTOL aircraft, and then try to analyze this configurational effect, which comes into play because of the eVTOL aircraft having multiple rotors juxtaposed in a particular arrangement around the aircraft. And if you could come up with these two correction terms, then perhaps you could relate the velocities in the outwash created by an eVTOL aircraft to the velocities created by a helicopter under the same circumstances. The disk loading effect is pretty straightforward. All you do is you divide the outwash velocity given by the one aircraft configuration by that given by the other. So typical values would be between 1 and 2 for those particular, for comparing classic eVTOL aircraft to normal helicopters. This configurational parameter is the more difficult one to determine, and that's where the study actually focused itself. Now, when you try to compare two aircraft with different configurations, you need to be really, really careful that you're comparing apples with apples. So we need a design taxonomy that actually makes sense from an aerodynamic point of view. We need to enforce a whole bunch of scaling laws to make sure that when we're comparing the characteristics of the eVTOL aircraft to a helicopter, we're not comparing apples with pears. So what we did throughout the studies, we devised a set of configurations, a taxonomy, if you like, or a hierarchy of vehicles, where the one would be a permutation of the next, but in a very systematic way. And in devising these permutations, we would make sure that certain parameters were kept constant throughout. So most importantly, the disk loading. So in other words, the rotor area depends on the individual rotor area depends on the number of rotors. We would keep the rotor geometry the same so that the rotor solidity would remain the same. And we would keep all the rotors operating at the same thrust coefficient. And if we do these three if we keep these three parameters constant, then we can be sure that we can compare cases with each other. We can do various parametric changes. So, for example, we can explore the effect of changing the rotor geometry. So we can go from, let's say, a basic lift cruise configuration. We can break the symmetries by moving the rotors outwards, as in the second example there, or we can do even more damage to the symmetry of the system by moving various rotors about, as suggested in the diagram at the bottom there. And the idea there was, can we actually pick up the effect of these changes of geometry in the pattern of outwash on the ground? Are there better configurations than others, for example, that produce less outwash? Is there bad aerodynamic practice? Is putting rotors in certain positions on the aircraft not such a great idea compared to other potential configurations that might be adopted? And can we actually offer design guidance eventually to the designers of these sorts of vehicles? So we managed to get through, in the course of the project, we managed to get through a few configurations, but certainly not a comprehensive range of them. So we analyzed a few conventional helicopters, this one with a conventional disk loading, this one with a slightly unrealistic disk loading that's more representative of eVTOL aircraft. And we looked at a range of lift cruise designs, we looked at a lift jet design, and we also looked at a more conventional quad rotor design in trying to compare the various characteristics of these vehicles. Now, how we did this is we went through the whole process using high resolution numerical models. So the basis of the results that I'm going to show you here is essentially numeric. But what we did is we used a very specific numerical tool called the Vorticity Transport tool, Vorticity Transport method. Now, the difference between that method and other more conventional CFD techniques is it actually preserves the inherent structure of the flow. And this turns out to be really, really important when we're trying to find out what the characteristics of the outwash happens to be. So a typical RANS CFD method would diffuse all this structure and leave you with this very bland outwash field, which would be created out across the ground, where you wouldn't actually be encapsulating some of the fundamental physics that we found that really drives some of the really, really important salient features of the outwash field. Okay, so remember that what we're doing is here, we're looking at a very specialized numerical method, which is optimized for the analysis of rotor flows with vortices, where, of course, there are these inherent instabilities that are really important to evolving the flow. So typically, this is what a calculation would look like. That's a very simple calculation of a two-bladed rotor, but you can see that we're actually capturing the tip vortices. We're capturing the interaction with the tip vortices, that they roll up and destabilize themselves. And then we're capturing the interaction of those tip vortices with the ground as they then spread out across the ground. And you can see how the flow actually starts to develop. But the flow has, if you like, it has finite range of dispersion out across the ground because of these inherent vortical instabilities within the flow. Okay, so we can identify the origins of flow structures using this high-powered CFD technique to analyze the flows of these sorts of systems. And that's typically what a developed outwash flow will look like. Here's the rotor, here are the tip vortices. They interact with the ground and they start to disperse and break up and destabilize themselves as they move out across the ground and give you some very interesting flow patterns. And you can see how different that is really to this classical conception of how the outwash flow looks. There's not really this well-developed jet-like structure that you might imagine from pictures like that from Preston's work. So the first thing, of course, is to validate these models, to compare against experimental data. And we managed to do that fairly successfully. So this is small-scale information from wind tunnel tests, where you can pick up the positions of the vortices. And yeah, we can pick up the positions of the vortices fairly well. This is a comparison against full-scale data for CH53, and we can actually pick up the variation of outwash velocity with distance above the ground fairly well in terms of both its magnitude and its character. Now, let's get back to this idea, the simple conceptualization of the flow. And that is this idea that the flow in the wake tube accelerates down below the system. And unfortunately, this is the characterization that is preserved, if you like, or supported by many RANS calculations. So you need to be a little bit careful about what you read in the literature. The flow is not actually like that. We know that the flow is much more granular. It consists of these tip vortices, and these tip vortices eventually destabilize. And then the structure below the rotor wake actually dissipates. It turns into this turbulent mush of fragments. And that's very, very different to this coherent tube of flow, which extends out to infinity below the rotor system. The vortice is inherently unstable. And what that does is it means that our conceptualization of what the rotor wake does should change in the light of this instability. So the wake consists of a portion which is initially coherent. That coherence disappears as the wake is destabilized by these inherent instabilities. The wake eventually ends up in this disordered state and then eventually decays into like a turbulent jet, which extends out to some distance below the rotor system. Okay, and this conceptualization actually resolves several of the paradoxes that are inherent in the simple model for the outwash that perhaps folk are slightly more familiar with. So how's the outwash field generated? Well, all I do is I take this particular picture over here for the helicopter rotor, or the eVTOL rotor in free flight out of ground effect, and I stick in a ground plane. Now, the kind of outwash flow that I'm going to get, given what I've described to you in terms of the changing structure with distance below the rotor, you can imagine changes depending on how high the rotor system is above the ground. So if the height of the rotor system is roughly equal to its diameter or somewhat higher, then I'm going to end up with a turbulent outflow across the ground. But if I bring that distance closer, then the interaction of the ground becomes ever more structured. So here in this case, I have a short distance over which these vortices actually remain coherent. So a region where we might call the ground interaction intermittent before you end up with this turbulent outflow. And if the rotors are really, really close to the ground, then you end up with a highly structured interaction with the ground. And I'll show you how that applies to different aircraft in a second. If you start to stick multiple rotors next to each other, you can imagine again the form of interaction then depends on how high those rotors are above the ground. So for a highly mounted pair of rotors, you can see that perhaps the interaction becomes turbulent, whereas if we bring the rotors way down close to the ground, then that interaction becomes far more structured. And you can end up with really interesting permutations of that. So for example, if you've got one rotor which is very close to the ground and one rotor which is really high, then you can end up with these sort of undercutting type features where, let's say, the wake from the low rotor manages to tunnel its way under the wake from the high rotor, and you end up with some very, very complex vortical structures, which I'll show you in a second. Okay, so the aim is eventually to get to design guidance, and I won't labor the slide too much, except to say that you can see, for example, from this example, which is described in a lot more detail in the cap, how, for example, the configuration of the aircraft might actually influence the kind of the structure of the outwash field that you might get. So an aircraft with low, large rotors might end up with a very different outwash pattern to that generated by an aircraft which has higher mounted, smaller rotors when operating at the same height above the ground. And perhaps the best thing to do is to show you some animations of just what goes on in that particular case. So using this numerical method, we can do a numerical simulation of the outwash from under an aircraft, where the configuration of which we've defined, and we can then pick up the various salient features to try to understand just what's going on in the outwash field. Okay, so how does the geometric configuration of the aircraft influence the shape and strength of its outwash field? That's really the question we're trying to answer in establishing the equivalence between helicopters and eVTOL aircraft. So let's have a look at a few particular examples. This is a jet lift aircraft where we've got these long slot-like effectors mounted around the aircraft. And what kind of outwash field it produces is shown in this particular video over here. You can see the outwash from the various rotors, or the various effectors colored in different different colors. We're looking at the vorticity field here, and you can see how that vorticity field spreads out across the ground. And the character of the flow in front of the aircraft consists of well, it is very different to that behind. You can see the flow behind the vehicle is highly turbulent and granular, whereas the flow out in front of the vehicle is fairly smooth and sheet-like. Something very interesting is going on along this axis over here. Essentially, what's happening at this interaction is you're ending up with a high-velocity jet-like flow out along the axis of the aircraft. But bear that in mind, and let's change the configuration. Let's go to something that's more akin to a quadcopter and see what kind of outwash that produces. And if I run that same video here, you can see that we end up with a situation really interesting, where there's a lot of interaction between the rotors. These rotors produce flow fields, well, bits of vorticity which tend to be sucked into the other rotors. You can see again, we've got this idea of a sheet-like flow out in front of the system and a much more turbulent flow behind, because in this case, these rear rotors were actually mounted higher above the ground than the rotors in the front of the aircraft. If we change to something which is a little bit more representative of conventional or the sort of, what would you call it, the very characteristic of a lot of the aircraft that we currently see on the design boards, then the character of the flow changes completely. So here we have an 8-rotor lift cruise configuration, and if I run its calculation, then you can see that the aircraft very quickly becomes enveloped in a highly turbulent outwash field, which is largely a result of the rotors being much smaller and mounted higher above the ground. Okay, so cutting to the chase, how do we take that information? Well, the first thing we can do is we can try to understand what the physical mechanisms involved actually are. And the interesting thing to do is because the calculations are unsteady, they run from an initial condition and they advance through time for as long as you'd like, you can actually pick up the evolution of the flow structures in terms of these inherent instabilities within the rotor wake. So this is the quadcopter at a very early stage in its history, and you can see the flow is very nicely structured. But very soon, these nice little interfaces, if you like, between the wakes that are created by the individual rotors start to succumb to these vortical instabilities, and they become ever more crenulated and disordered, until when you start to look at the flow at a fairly long time after the flow has started up, most of the structure in parts of the flow is broken down, and these vortex instabilities are very much taken over. Okay, you start to see the effects that you'd expect. So if you change the height of the aircraft above the ground, in this case, this is the lift jet aircraft, you can see for low altitudes above the ground, you might end up with a coherent, very sheet-like outwash field. But as you increase the altitude above the ground, that outwash field turns into a much more turbulent interaction with the surface underneath. Likewise, if you change the forward velocity of the aircraft, you expect to see the Curtis diagram type effects, where in this case, this is the quadcopter. In that case, you can see the aircraft is almost enveloped inside its recirculation zone. As we speed up the aircraft, a ground vortex forms, and as we go ever faster, that ground vortex gets swept into the flow behind the aircraft. Much more prevalent or easily observable in the case of the lift jet, where the propulsors are higher above the ground in that particular case. Now, this figure is perhaps one of the most important ones that I'll show you, because a lot of the data for the velocity in the outwash field is in the current literature is presented as a mean outwash value plus a superimposed perturbation, this idea of the outwards flowing jet of air across the ground. And if you have a look at this simulation of what the instantaneous velocity on the ground actually looks like below an aircraft like this, it's very hard to imagine really that there is this coherent jet of air across the ground upon which we can superimpose small fluctuations. The flow is highly unsteady. It consists of these little cells of velocity which travel outwards across the ground at various rates. Some cases at up to 3 times the induced velocity through the rotor, but there's no real idea of this kind of analysis here. So one of the conclusions of the study is we need to be really careful of that kind of analysis of the system. Okay, but if we go through the motions, if you like, then we can come up with a diagram something like this, which tells us just how much the outwash velocities within an eVTOL's flow field will exceed that of a conventional helicopter with conventional disk loading. And these figures are there in the cap, and you can look through them in more detail. But essentially, if you do analyze in terms of the mean velocities, then you start to see things like the lift cruise configuration, because of the way its rotors are juxtaposed, is quite easily capable of producing twice the kinds of outwash velocities in the mean that a conventional helicopter with conventional disk loading would produce. If you look at the unsteadiness of the flow as measured by the RMS velocity, then that figure goes up to something like 3 times the amount that you might expect from a conventional helicopter with conventional disk loading. So these are the sorts of figures that you might initially be interested in, but there's further interpretation that you can actually do of this information. These are just the maximum values as experienced somewhere within the outwash field. Let's have a look in more detail at the structure of the outwash field, and this is where things get really, really interesting, in that the velocity distribution that is produced by these various eVTOL configurations is very, very different. So if we look at the mean flow in the outwash, then you can see for the quadcopter design, most of the outwash is concentrated in a jet which is actually aligned with the vehicle's fuselage. And that's largely a result of the interaction of the rotors with the fuselage as a matter of interest. If we look at the lift cruise configuration, then we tend to find that the mean outwash moves. It's more laterally directed as a result of the squeezing of the flow between the fore and aft rotors in this particular case. If we have a look at the RMS velocities, then we can see that the RMS velocities are concentrated in these very distinct jet-like structures at particular orientations with respect to the aircraft. And those orientations are generally aligned with the confluence between the individual wakes that are produced by the individual aircraft. Now, in my opinion, it's these jet-like structures which are perhaps the most interesting features of the outwash that is produced by eVTOL aircraft, because those will have the most consequence for operations near vertiports and for passengers and infrastructure that happens to be close by to the vehicle during its operations. The other interesting thing is if we change the configuration ever so slightly, we can make some very big changes to the configuration of where these jets actually exist and how many of those jets there actually are. So these diagrams over here compare our very symmetric lift cruise configuration with one where we've actually moved the rotors around the configuration a little bit to try to optimize some of the aerodynamic interactions. And you can see that the jet positions change quite considerably in terms of where they are around the azimuth of the vehicle. Okay, so what does this all mean practically? Let me try and summarize in a few slides as to where this is all going. Well, what we do now know from these simulations, or what we very strongly suspect, is that eVTOL aircraft in general will generate, first of all, a stronger outwash than comparable helicopters, but also a far more directed outwash in terms of the existence of these axes along which the flow will be very, very strong. Whereas with a conventional helicopter, you expect the outwash to be more or less consistently a certain value, no matter what azimuth you happen to be approaching the aircraft by. Okay, so what is that really going to mean? Well, I'll skip over the slide to a large extent. The first thing is to point out is that you need to use the right numerical methods to pick up these flow features. If you use a conventional RANS flow, you tend not to pick up these jet-like features, because the basic physical mechanism that produces these jets is the interaction between the vortices on the ground. And most of your conventional CFD codes don't resolve the flow to that extent to be able to pick up these jets. So using the appropriate tools is perhaps the first recommendation that I would make. But when we come to vertiport design, of course, we know that the current way of dimensioning vertiports is in terms of the controlling dimension D of the aircraft, which is just a geometric characterization of the size of the vehicle. Now, the argument here is that it's a good approach to start off with, but if there's aerodynamic interaction involved, then that controlling dimension, which is based simply on the geometry of the aircraft, is insufficient. It acknowledges aircraft size, but it doesn't actually acknowledge the aircraft's configuration itself. So it ignores issues of disk loading, and it ignores the directionality of the outwash. So if we're going to use these sorts of principles, which, okay, are largely developed in the context of protecting the aircraft from its surroundings, but there's a tendency within the vertiport design community to extrapolate this kind of analysis and use it to try to determine the zone of influence or the zone of danger posed by aircraft on the surroundings, then we need to be very, very careful in using this controlling dimension analysis. Another thing to realize is, of course, is that the orientation of these jets is dependent on the orientation of the aircraft. The jets essentially move with the aircraft as it turns and maneuvers on the ground. And hence, this poses quite a few issues once we start to consider issues such as ground handling and taxiing, passenger access. Air is invisible, so we need to make sure that the passengers are not approaching the aircraft along these zones of elevated outwash or are not being interfered with by another aircraft that is operating nearby. And then ground weight, turbulence, and upset to following aircraft is a whole other can of worms that perhaps I'll deal with in a later bit of research. Measuring the outwash field is crucially important here. How the aircraft is certified in terms of the outwash characteristics. The diagrams over here show the EASA proposal for measuring the outwash. And what they do is they essentially set up a series of probes at a certain fairly ad hoc distance from the aircraft and fairly ad hoc distance apart. And they require information to be obtained at various heights and distances from the aircraft. Now, I think when we go forward and actually understand the outwash characteristics of these aircraft in proper detail, we'll realize that this fairly ad hoc approach is not particularly well informed and perhaps not appropriate. And we need actually to use the physics to define just where we measure the outwash characteristics of these particular aircraft. So I think as far as OEMs and regulators are concerned, there's a danger here that we follow the letter but not the spirit of the procedures. So we take an aircraft, we go through the standard procedure, and we quantify or qualify the aircraft based on a standard procedure. And the salient features of the field are going to be missed if we do something like that. And we'll actually probably underestimate outwash velocities, particularly if the sampling regime is not dense enough on the ground around the aircraft when we actually try to quantify the outwash features of the aircraft itself. One thing that we really also, I think, need to take into account is that a lot of our current experience is based, especially in terms of analyzing the human effect of the outwash field, is based on physiological effects which are derived in the context of fit, strong individuals. So, for example, the Paxman model is really to do with US Marines, tough, burly guys carrying huge backpacks, and how the outwash created by large military helicopters will influence those particular individuals. And of course, this idea of a statistical view of the outwash field on which the Paxman model is based is outdated. It characterizes the outwash as a steady stream with these superimposed perturbations. And hopefully I've shown you that the flow is much more granular than really can be supported by that particular mindset when you start talking about the outwash velocity itself. And of course, most of our customers for these vehicles are not going to be burly US Marines carrying 80-kilogram backpacks. They're going to be grannies and children. And as a result, we perhaps need to change our emphasis in terms of our modeling of the environmental impact of these vehicles to actually take into account properly the physiological characteristics of the most vulnerable of likely passengers in terms of their response to fields which are going to actually be very different, perhaps in character, to those that are created by the helicopters with which we're somewhat more comfortable. And so in summary, and this is my last slide, there's definitely evidence to suggest that the outwash will be a more serious problem for eVTOL aircraft than it is for helicopters. And I think we can learn a lot from past experience, but within the community, quite often you come across this idea that eVTOL aircraft are just helicopters in a different guise. And that's not entirely true. There's a lot of additional information and science that we can bring to the table to analyze the outwash problem. eVTOL aircraft have their own specific issues. And certainly I think that prevention is better than cure, that we should seek heuristics and general principles that we can apply to the design of the vehicles in their earliest possible stages. Can we bake in good design principles early enough in the development process so that when it comes to certification, it's a walk in the park because we actually understand the physics and we've designed that physics into the aircraft from first principles. And I think in terms of the flight testing and certification community, these are going to become more pressing issues, of course, for the eVTOL community. And when we do that, certainly I think as numerical analysis will have a big role to play, because if we can do that proper detailed aerodynamic analysis right from the get-go, we can actually help in that certification procedure and help make aircraft such as this a lot safer than they might be in the absence of that deep physical understanding. So really, it's a very quick canter through the work that we've done. Hopefully, I've left a little bit of time to answer any questions that there might be. I'll stop sharing right now and turn over back to Al for any further interaction that might be appropriate.
Wow, thank you. Amazing how fast you did that and how cleanly, and you got all the way through it. So thanks for that. That was pretty slick. Yeah, so it's noon. I know a lot of people are going to have to jump off, but we can just keep running. We'll have some time for Q&A, and we'll record the session. So if any of you can attend the Q&A now, you come back and watch it later on. So I see Rory, you got your hand up. Why don't you go first?
Yes, Richard, thanks very much. I guess maybe a couple of comments and then one or two questions. And
Sure.
I quite enjoy being referred to as a burly U.S. Marine with a backpack, but I sponsored research previously focusing on rotor outwash, and you can see it there in the icon picture across a range of CPs and CTs. And we use helicopters as surrogates, but restricting the outwash field, and we were investigating the effect that has on the power required to fly the vehicle in proximity to restrictions. And then from that also kind of interested, I can connect you with the principal investigator for it, and the lead test pilot was actually an Empire Test Pilot School graduate, and I did participate in the flight test, and I did find it very interesting. Yeah, it was done at Naval Test Pilot School, and they have probably 10 years worth of data to analyze as the answer I'm hearing back from them. A couple of questions on the methodology. I noticed at the beginning, and maybe I missed it, you talked about disk loading being your normalizing factor here across different configurations. But then at the beginning, I thought I heard you say that disk loading may not necessarily have the same influence on the outwash, in that the disk loading for different vehicles can be the same, but the outwash flow field would be very different. So just something there that I had a question on. And then the other piece was, did you consider different rotor rotation directions, or maybe the simpler designs like the quadcopter, like we would have a choice of at least 2 rotational directions for quadcopter designs, and how would that influence the outwash flow field? Thanks.
Sure. Yeah. The first question in terms of the role of disk loading. So what I presented is like a 2-part equation, if you like, to make the transfer, if you like, from the helicopter regime into the eVTOL regime. And the disk loading certainly acts as a scaling parameter on the entire result that comes out of the analysis. So you separate that out into the front and you say, okay, we'll multiply by the induced velocity through the system, which is proportional to the square root of the disk loading. But then the second term in the equation takes into account the size and shape of the vehicle. So that was the term that we were largely trying to evolve, or to gain a handle on during this particular study. It was to say, okay, given that there is, first of all, the scaling by the disk loading of the system, how then does the shape and size of the vehicle actually influence the argument as well? And so hopefully if you look through the recording, you'll see this KC term, which is this configuration factor, and that actually takes into account size and shape. And then we multiply that by the disk loading to end up with the actual transfer from the one system to the other. In other words, to do the comparison. Hopefully that answers your first question in some detail. The second question, yeah, different directions of rotor rotation. You know, the number of permutations here is endless. If we had infinite amount of time, I think I'd still probably be sitting looking at interesting configurations. But yeah, for example, direction of rotor rotation is one of the key parameters that might influence the shape of the outwash, because we know, for example, that the directivity of these jets is very much influenced by how by the direction of the vorticity as it comes into the confluence zone, and that is heavily influenced, of course, by the relative directions of rotation of the rotors on the system.
Thank you.
Thank you.
You're on, Peter.
Richard, great talk. Thank you.
Thank you, Peter.
How should we think about the potential of vorticity to cause problems with a person, as opposed to some sort of measure of average power or peak power? You know, what I'm trying to connect your very valid statement that averaging out the vorticity hides important data, but I'm also trying to understand why a mean jet value plus perturbations isn't sufficient to think about potential harm.
Okay. Yeah, that's a great question. It gets to the heart of the matter. So what would be a good analogy would be imagining standing in a river. So you're standing in a river up to your waist, and all of a sudden a wave comes along. If that wave is just a perturbation to the depth of that river, you'll probably not even notice it. It'll pass by, and you'll already have been braced against the river, if you like. And so being influenced by the wave is not that much of an issue. But now, where you have these discrete vortical structures, there's the whole situation is a lot more violent, if you like. The interaction's a lot more violent than that. It's like being run over by a breaker that's coming past you in the shallows, mind you. So it's largely to do with the physiological response of people to these kinds of flows. It's if you can imagine sitting in a wind which is already at, let's say, 20 knots, and another 10 knots comes along to give you an extra little bit of a buffer. It's very different to being exposed to that 10-knot wind from a standstill, especially if you're an infirm or aged person.
So it's a power question based on the rate of onset of the change.
This is something that's the one issue. So it's this idea of rate of change is actually very important physiologically.
Yeah, it's like the old adage. It's not the fall that kills you; it's the sudden stop.
Yeah, exactly. In this case, it's the sudden. I'm kind of arguing it's the sudden onset, if you like, of the whatever leads to you falling over. But more importantly is that video that I showed you of the structure of the velocity field. If you look at a single snapshot of the velocity field, it gives you no impression whatsoever as consisting of, let's say, a nice uniform stream with perhaps a slight ripple on it. It's nothing like that at all. It's more like, if you're a yachtsman, you'll kind of understand this. If you're trying to sail on a very calm day, the flow, you sit in the yacht and nothing goes on for a while. Then all of a sudden a gust comes and wham, and you're over and you're in the water. And that's very much more the character of the flow that you see out of these vehicles. Now, of course, speed that yachtsman process up by a couple of orders of magnitude to get the kind of rate at which these cells traverse out across the ground. But that's really what I'm talking.
Okay, got it. Thank you.
Is taking this whole concern and flipping it inward, does all of the outwash and these concerns affect stability and control of the aircraft? Or is it more you're concerned about the pedestrians and the vertiport environment?
We're really concerned with both. So I didn't present much information for the influence of the outwash field on the aircraft itself. But in some of the simulations that I showed you, there's definite evidence for that. So what you'll find, for example, is that the outwash field traverses out across the ground plane, but is very, very deep. So deep, in fact, that an empennage, which is not properly protected from those effects, might get wrapped up in some of these vortical structures as they propagate out across the ground. In that case, you'd find buffeting. In the tilt rotor field, they talk about things like fountain flows and suck down. You see all those sorts of features very clearly in some of the simulations. So yeah, there's very much this idea that the flow comes down from the rotor, spreads out across the ground. But so, for example, where there's a confluence just below the fuselage, there's a tendency for that flow then to pop up and interfere with the fuselage and create all sorts of interesting dynamic perturbations to the vehicle itself. So those need to be controlled in some way by design or by some other methodology.
Well, we certainly hope that this venue that we have here is a place for people to talk about that. We haven't heard much about aircraft suffering from, for instance, RPM controlled propulsors not having the bandwidth to keep the sunny side up. We haven't heard. Yeah. Hopefully, if things start to pop up, we'll all talk about it. What do you got, Marty?
Yeah, I really like your discussion about how the D factor for vertiports is probably not substantial enough. an interesting thing, and I expect you'll probably be doing this ongoing research, is looking at wind azimuth effects on those safety zones also, because that can be very pronounced.
Absolutely.
I like also the ground model, the modeling of the ground vortex and its effect. As a wind azimuth in the V-22, we saw a pronounced suck down at 20 knots due to ground vortex.
Yeah,
To
I
the
can well
point where
imagine.
it made automated landings almost impossible because you couldn't anticipate it until you were very low to the ground. So I think what you're doing here is fantastic, and
Thanks,
really,
Shimon.
really looking forward to some more work here.
Hey, I have a question. Can you hear me this time?
Now we got
Yes, perfectly, actually, this time.
Okay. I had asked the Revolutionary Vertical Lift Technologies project at NASA about downwash, outwash testing that they had done as far as sensor set for, ground sensors. And they obviously did a lot of work for that for Rotorcraft, but they said the sensor set obviously needs to adapt to the configuration of the vehicle, and they haven't put any resources in identifying a design for that. Is that something you guys have investigated?
It's certainly potentially a next step in that it's one of those interesting problems. It's in that often occurs in science, is that if you don't know what you're looking for, or you don't think you're looking for something, you'll never find it.
Yeah.
And here that's a particular case in that if you have a sensor matrix which is not refined enough, that's not looking in the right parts of the flow, you're just not going to pick up some of these pertinent effects. So the idea here in the UK is that using these simulations, we will try to define a suitable sensor array for measuring the outwash from a particular aircraft with a particular configuration, and that's going to be an important initial step, I think, in deciding how you actually go about quantifying the outwash that's created by any particular vehicle. There's work in progress, certainly, at the moment.
Yeah.
Okay, who's next? Anybody else got questions? Okay, 3, 2, 1.
Just out of curiosity, Dr. Brown, I had to have one. Your vortices, do they grow in size as they get more far away from the rotor?
Okay, I need to be careful what I mean by growing in size.
In diameter, the diameter of the vortex.
Yeah.
I didn't...
Okay, so okay, so these vortices are subject to one of the most interesting instabilities that these vortices are prone to is catching up with each other and then evolving around each other. It's called the leapfrog instability. And what that instability does is it gathers up individual tip vortices and turns them into more complex, stronger, more powerful features.
Mm-hmm.
So where we discovered those, more interestingly, is actually in our studies of brownout, because it's actually these very, very strong coagulated vortex structures that are responsible for creating like these columns of sand that tend to rise up into the air. The brownout field's not homogeneous either. And it's this coagulation of vortices into these larger structures which can be responsible for some of the detailed features of the brownout cloud as well.
Interesting. Thank you.
Okay, Al, I got a question.
Hey, go Rex.
Richard, in looking at what the research you've done to date, one of the things that we look at in the evolution of eVTOLs as it currently relates to helicopters is the wake turbulence. And one of the things is we look at airlines, airplanes, and heavy jets and the wingtip vortices they create, and we understand those. We know that helicopters produce wake turbulence, and we understand that we need to avoid that. One of the questions I had was, are these vortices and wake turbulence that is generated, are they staying intact for a particular length of time? That was one of the things we discovered with wingtip vortices, is they're invisible threats that stay intact for a very long time. And I didn't know if you'd seen that increase, decrease, or exactly the same.
So yeah, you do end up with these very persistent vortical structures in the wake behind an aircraft, which is traveling at, especially when they're traveling at fairly low speed. And the power within those vortices is greater than if, for example, you're going at high speed through the air. So yeah, it's much the same as in the helicopter case. I think for a long while the the importance of wake interactions in the helicopter community was a little bit underplayed until there were a few rather high-profile accidents. And that's certainly an area which I think in the eVTOL community needs a lot more careful observation. The wakes that are produced by eVTOL aircraft are a lot more complex in structure even than those that are produced by helicopters. And we need to understand where these individual vortices go, how they coalesce, how they propagate across the ground and through space, and for how long they are persistent behind the aircraft. And I think that's a big area for future development.
No, that'll definitely drive the spacing and separation criteria. And I have a feeling that some of the throughput models we've seen to date may not hold up.
I think I would agree with you, Rex. Yeah.
Thank you, Richard. Great stuff.
Thank you.
Okay. Any other questions? So, Dr. Brown, what is next for you in terms of your next research effort? Is more of this? Or are you switching to something else?
Yeah, I think, I think I'm motivated very much by the idea that science can contribute to the safety of eVTOL aircraft. And the more we know about the aerodynamics of these vehicles, the safer and we can make them, the better we can design them. So the two big issues that I think, and they're as I showed, they're interrelated, are vortex ring state and the outwash characteristics of these vehicles, with, of course, the wake turbulence issue being kind of sitting in the middle to a certain extent. So yeah, there's
more to come.
I hope the one thing that I didn't kind of present is the idea that this research is kind of over and done and there's nothing that anybody can contribute. There's a tremendous amount of additional work that we still need to do in terms of characterizing even the outwash field that's produced by eVTOL aircraft in general.
Okay.
So maybe an update in a year's time. Let's see where we are.
All right. Well, thank you once again for taking the time to talk to us and to give us the lowdown and all these concerns and so forth. I think